Welcome. Today I want to introduce you the foundations of convolutional neural network in deep learning. On the way, I want to quickly review the modeling strategy which I did last time, and of course, introduce you the CNN basic, convolutional neural network basics. Again, we'll talk about overfitting, underfitting, which I did last time, bias variance trade-off, regularization techniques, and assignment to HTML review. Finally, I will also give you an introduction to transformers in deep learning. So last time I did bring this particular slide that gives you the overall modeling strategy under broadly called ML ops. So there are 4 stages to it. The formulation of the problem is often more important than its solution. That's by Einstein, and it's no wonder. And that's why this section is very, very important, and you will have to work with your senior managers or your other department people who might be coming from the business side to understand what is the problem that we are trying to solve. But you need a tool to start that, and that's where the dashboard comes into play. So the dashboard is your tool that helps you to figure out what is the right problem to solve, working along with the business managers as well as possibly other departments. Okay, and that will help you to formulate your needs on data requirements and data strategies, which in turn will get you the data. But then once you get the data, you have to do the data quality and EDA to figure out how to fine-tune your problem and generate the features that are relevant for your problem. I just want to recall this Yogi Berra statement. You can see a lot by looking. So visualization matters a lot. And then that should lead you to analysis and modeling. Einstein says models should be as simple as possible but not simpler than necessary. So that's where you bring in the ideas about what is meant by a right model, okay, where you will talk about the bias variance trade-off and as well as the training error curve versus the validation error curve. Remember, you have 3 types of samples: training, validation, and testing. Of course, they all come from one big sample. Training you split around, let's say, 60% or 70%. And the remaining, whatever you have, 40% or 30%, you split it equally to between validation and testing. So you use the training and validation to build your model, and once you are satisfied with the best model, by looking at the bias variance trade-off curve, you go and apply it for the testing sample, and whatever you get as the performance is the best performance you can get. Okay. So that's a kind of up to the ML ops, up to the analysis and modeling, but then you have to present the conclusions, get a buy-in from the senior management and other departments, implement it, follow through, monitor the model, and then get back the results back into the dashboard and see whether your questions are getting answered properly. If not, you will have to do another iteration in the next step. Very important step. It comes broadly under ML ops. And then we talked about the importance of hidden layer in the last session. So you have an input layer, and there is there could be any number of hidden layers. You experimented in assignment 1, multiple ways of defining various hidden layers. Hidden layer 1, 1 hidden layer, 2 hidden layer, and so on. And then the hidden layers do not have to be of the same number of neurons in each of the hidden layers. In fact, you will see there is some advantage, especially in deep learning, where you have lots and lots of data at pixel level. You need to reduce that number of neurons into lower number of neurons, and it's an indication here. We reduce the lower number of neurons, and then using the lower number of neurons, you want to predict the outcomes. Okay, and in this case we are saying there are C outcomes, W1, W2, WC classes, and then it's a reduced number of, we are not talking about only 2 neurons, remember there's a dot dot dot, so it's a reduced number of neurons, and using the reduced number of neurons we predict the, that is called a fully connected layer, and at that time you use the multi-layer perceptron model, basically input to the output connection. And if it's a classification problem, we use what is called the softmax, and the softmax is basically a multinomial probability distribution, and this is the structure of multinomial probability distribution. Okay, and so wherever you have the maximum probability for a given sample, that takes the class to be the predicted class. And the loss function that we use in the classification problem is what is called the cross entropy, which is minus summation of the product of pi times logarithm of pi hat, and the pi hats are coming from your samples. Okay, so that is the kind of recalling the structure of the deep learning model. This is the structure of deep learning model. Remember that. Okay, and specifically, how are we going to apply it to images, where we will the terminology that defines is what is called the convolutional neural network. So we are going to do something called convolutional computations. Convolutions is basically inner product, and we use not only inner product of the input values with the weights activation function that gives you the output value, and then we do some kind of another transformation called the pooling. Pooling is same as pool the values and select some specific value. Usually it's called max pooling. Okay, so let me go one more time, more specifically. So if we are talking about an analysis of this image and we want to know whether it has a boat or not, we will scan through what is called a kernel function. This is an area is called a kernel. Okay, an area is a kernel, but not only we have an external matrix kernel which has zeros and ones, for example. It can be any other value, but zeros and ones are common. Zeros and ones, and we scan through the regions here. Slowly we scan through, and when we scan through at a particular point in time, you take the inner product of the values of the kernel matrix with respect to the image values. Okay, the inner product means basically summation of the product sum. Okay, or some product, some of the product values of the kernel feature or kernel function. Kernel is also a feature. So I will come to the what kind of features to use, but basically 0 ones of the matrix of values that are scanned through. As you scan at every one pixel movement, you take a cross product, sum product, of the values of the kernel matrix values with respect to the image matrix values of the pixel values. So that will give you reduce the number of pixel values into another matrix like this. Okay, and the convolutions are done usually with a ReLU function. Remember, reduced linear units. Rectified linear units, of course it does a reduction, but rectified linear units. So the sum of the values, if it is positive, so positive, you take the positive value. If it is a negative, you take it as 0. So obviously this function will have negatives and positives. This particular feature kernel will have a positive value and negative value in a certain way, distributed in a certain way. So the question is, what kind of, there are so many ways you can fill up, a kernel matrix with negative values and positive values, which value to take, right? So you just have to try different things. One way is to find out where the diagonals are, getting positive values and off diagonals are negative values, or the upper right triangular values are all positive, lower triangulars are negative, and so on. So many different ways you can do. That's why this is a highly computational problem. Okay, the convolutional neural network is in general, deep learning is a high computational debt that you have to you will create, but that's part of the game anyway. So it is the inner product of the kernel with respect to the that level of that part of the region of the image, and you keep sweeping that all over the images. So you will start here. If it is a 28 by 28, then let's say you have 4 by 4 kernel. So 4 by 4 kernel can have let's say all off diagonals are zeros and diagonals are 1. Then you keep moving, okay, and so you will reduce this image 28 by 28 into 7 by 7. So that's why the reduction in the size of the image comes. But then it picks up wherever it has diagonal type, like this kind of features, where it is very strong, the slanted line type features are there. It will pick up very clearly by this particular kernel feature, okay, which is scanning the image. So or it could be some kind of a, let's say, oval shape. So in that case, you have to create a oval shape kernel feature in the kernel matrix data that you are talking about. So the ovals will have the ones, the outside ovals will have negative values. That way, your ReLU will capture those regions which are having high signals in those in the images. So now it is reduced. So now out of this, you might take a smaller region again, and and then you will find out the maximum, where the maximum are. That is called the pooling step, also called max pool, and that is what reduces here. So that is in 28 by 28. 28 by 28 became 7 by 7, and then you doing the max pool, let's say 2 by 2. Then it is very close to, it's not exactly divisible by 4. 7 is not divisible by 4, but you will end up something like 2 by 2. So sometimes you cannot do a padding also. If you don't have exact number, you can do a padding. Left side you have only you add, so you may have only 3. You may, even though it is have a 2 by let's say 4 by 4 across the 7 by 7 image, then across 7 by 7 data, then you may include the first row. So you get it, first one is 3, and then you keep moving, and then you will get the maximum values, and that's called the max pool. So you reduce this and keep reducing, continue to do the convolutions and max pooling, and then finally you'll get only one single valued neurons. Okay, that is what is called the fully connected layer. You can do the fully connected layer with another, remember, hidden layer here. But the main point is, once you come to the fully connected layer, it becomes a multi-layer perceptron. Okay, using the multi-layer perceptron, you know how to solve the problem and apply that one. So I have to finally find out whether it's a cat or dog or boat or bird. Okay, so the maximum, let's say, for a particular sample, it happened after you build the model. After you build the model, for a particular sample, it turns out to be the max. The soft max value is 0.94 for boat. Then you say that that particular image has a boat. Okay, so the only thing, additional thing that I'm bringing in for today's discussion is this, what is called the convolutional operation, which is the inner product calculations of a feature, which is a two-dimensional feature, which is a matrix values, which is supposed to represent the edge values of an image. Okay, so edge values are here, ovals, for example. Okay, and then ovals along with some kind of a line, vertical line. So those are all the features that needs to be represented in your feature engineering part of it. That is the kernel part of it, kernel definition part of it. So by applying these kernels of different types of kernels, you figure that out in terms of whether it's a cat or a dog or a boat or a bird. So I basically introduced you, you already know the MLP, the multi-layer perceptron, and I basically introduced you the convolution operation and the ReLU activation function, and also the max pooling operation. So we continue to use the cross entropy, which we talked about earlier. So that is exactly what is going on here again. So you can see that this is the filter, also called the kernel or contrast or the feature. So you run the filter around this one. Okay, you keep moving the filter around like this. So in this case, for example, the filter times this is the cross product, which is also called the inner product. You'd see that there's 1 here, 0, 0, because there's 0 here. There is only one so far, and then 0 here, 1 here. So I got 3 values, and also there is 1 4 value, 5 value. So there must be 3 by 3, 1 1 1, Oh, this is 0, this is only 1. Okay, so 4. That's why you get a 4 here. So this inner product with this one is, this times this plus this times this plus this times this, 1 times 0, 1 times 1 plus 0 times 0, like that, 1 times 1 plus 1 times 0 and 1 times 1. So summation of this, summation is 4. Okay, so you kind of scan this, the whole image. This image, you scan this one and you get this summation value. This is called the feature map. And so 7 by 7 with the convolutional filter of kernel filter 3 by 3 results in 5 by 5. Okay, so you reduce it like this continuously, and you will have eventually a fully connected layer, which is only single value cell values. So for example, if there is a feature like this in the picture, then the vertical filter will be, a good filter for this is, vertical filter is this one. As you move here, you can see this is going to capture this particular perpendicular values. Okay, so if you do so if you apply this, if I apply this vertical filter, it will give the output something like this, right? Because you move this, you keep moving this way, right? So first, this 3 by 3 is coming over this one. At that time, the inner product will become minus 90, this value. And then you move to this one, it will become 0. When it moves, this comes to this place, that means 1, 1, 1, 1 will have inner product value here. Then that will become 90. So, and then you go down one step and then start from with these 3. So again, it will become 90, 0, 90, and then finally these 3, minus 90, 0, 90 you will get. So the inner product of the convolutional part of 3 by 3 filter, vertical filter on this one will become like this. Now if I apply that again, if I apply the horizontal filter, okay, on the other hand, instead of vertical filter, if I apply the horizontal filter, you can see this is, inner product will become 30, and then, but this, this 0, 0 will become here 0, but here it will become minus 30, the summation of that is 0. So if you go over the horizontal filter completely, 3 by 3 the whole way, it is become 0, 0, 0. Next 3 by 3 whole way, it is 0, 0, 0. Finally, it is 3 by 3 will go, you'll get 0, 0, 0. So this is how the convolutions are happening. Just to gain you knowledge about how the convolutions are done, and it is really to capture the these are let's say these are kind of representative of the edge. Remember, these are the pixel values, and this is your filter. So filters can be learned instead of fixed filters, as well, and same filters are used to scan the entire picture. Remember that. And similar features at different locations can be detected using just one filter. It reduces the number of parameters basically, but in the end, it is really picking up where the signals are. So it is to reduce the size of the data and pick up where the signals are, and finally come to a some kind of a single neuron based multi-layer perceptron, and that is fully becomes fully connected layer. At that time, you use multi-layer perceptron, usual neural network solutions. Here is I also want to bring out the importance of covariance here, and its relationship to what is called the cosine relationship. Okay, so for example, if you have the data, let's say the 4 parts, the relationship, the relationship between x and y is in this way, so it's basically linearly increasing relationship between x and y. That is, as x increases, y increases. Okay, that's what this data means. And so let's use the algebraic signs so that so that I can explain this quickly better. The algebraic signs will be so here in one, in quadrant 1, for all the values in quadrant 1, y minus y bar is positive, because y bar is here, so all the values here will have y minus y bar to be positive. On the other hand, x minus x bar is positive for 1, but for 2 it is negative. So here x bar is less than this, so for all values here, x value is, let's say this, x minus x bar means it will be negative because x bar is higher than x value. So here it is positive, the y minus y bar, here it is x minus x bar is positive, but on the other hand here y minus y bar is again positive, but then x minus x bar is negative here. So here negative, here positive, here positive and positive, okay, here positive and negative, here negative and negative, okay, and here negative, y minus y bar is negative and x minus x bar is positive, right? So so here the cross variant, the cross product, right, y minus y bar, x minus x bar is positive is positive, negative is negative, negative is positive, negative is positive. So if you're talking about covariance, what we are saying is if covariance is greater than 0, then there is a positive relationship. This is what the covariance is, right? The covariance is, we just took only the 4 points, so if you do 10 points, 100 points, then overall what happens? You want to find out the summation. That's what this means here, and the average effect of that cross product value. So if the average effect of the cross product values of among x and y is greater than 0, then there is a positive relationship. If it is less than 0, it's a negative relationship affected by changes in the units of measurement. Okay, covariance is affected by the changes in the units of measurement. So in order to find out a correlation, you just want to standardize the data before computing the covariance. Then it's called correlation coefficient. Okay, so that's a relationship, covariance and correlation. It's a quick review here. So this is the correlation formula. It is between -1 plus 1. Convolution operation is computing correlation between image and filter pixels. In NLP, we use cosine similarity, which is similar to correlation coefficient. I will talk to you about that when we talk about NLP. Okay. So what we are saying is that convolution operation is computing correlation between image and filter pixels. Relationship between filter. So if you design the filters to capture the right relationship, you can really it depends on the filter, right? And if you do a right filter or right kernel, you will be able to get the quintessential signal parts of the image. That is the main point here. Okay, so by creating a right filter that is highly correlated with the signals in the image, then that means that the highly correlated, you will be able to predict correctly. Okay, so so let's go over convolution layer again one more time here. We talked about it, but I'm going to go a little bit more detail, because in the case of image, you remember it could be a color image, then it is a RGB, red, green, blue, and each layer has a certain pixel value, right? That's what when you combine them, it represents a specific color. A specific color is a combination of red, green, blue. Okay, so so in this case, let's say we are talking about 6 by 6, okay, image, 6 pixels by 6 pixel image. Then there is a red layer, there is a green layer, there's a black, blue layer, right? You can technically solve the problem with just, take a black and white version of it, okay, which means certain combination of RGB only. Gray is a certain combination of RGB. You can take it, black and white is certain combination of RGB too. So you can take just as one image and see its pixels and just model that one. That's the easy way. But here we are talking about an explanation if you have how to do RGB. So I will say the simplified method is convert it into a black and white and solve the problem. Okay, for now, let's take it that way. Unless color is adding to the discrimination part of the resolution. Okay, then you have to do multi-layer calculations. And then, the multi-layer calculation, again, you will do like what you did before, kernel application with ReLU, and so it reduces the number of the size of the image. From 6 by 6, it became now 4 by 4. And then finally, because when you apply the ReLU, you are only taking care of the positive values. So those positive values continue to be reduced into 2 by 2. It's called subsampling or max pooling. and then now this is used, to create a fully connected layer, and from fully connected layer you go and use the multi-layer perceptron solution method. So we continue to speak